People are still joining, but regardless, thank you everyone for joining today's session. My name is Dmitry Vinnik, and today we'll discuss the incredible world of concurrency. And I hope I'll be able to bring you back to it if you've abandoned it in the past couple of years. But first, I really like to establish the goals that I'm trying to achieve today with you guys. So first and foremost, I'd like to actually talk about the concurrency as a whole and different forms and shapes it can take, because it's been used and thrown around with interchangeably with parallelism, asynchrony, and concurrency itself. So I want to make sure we're very clear what is what. Then I'll talk a little bit about misconceptions of concurrency and ultimately try to debunk them. And the last part of today's talk will be focusing on the workflows in Java and how to use them and why do we even need to use them in the first place. But the first question you might ask, why do we even care? Why we would talk about the concurrency today? And this is fairly easy to actually argue about. The motivation is fairly simple. Obviously, first of all, nowadays all desktops, all laptops, or any machines would have a multi-core. Even the laptop I use today has multiple cores in it. The microservices are so abundant these days, it's not even a buzzword anymore. And obviously, the computing cloud services like AWS and Azure are so abundant that they drive half of the internet at least. And of course, you can't talk about the innovation and technologies without bringing up the Moore's law. But I won't talk about it today. So the conclusion you can just draw from these 3 points is that the concurrency is a new reality, and I would even go further and say that's a reality, that you can't really deny change in our world. And regardless of the environments changing towards the concurrency, you can still argue what's in it for you. Because the environment's changing, you might still want to stick to the old ways. And of course, I'd like to clarify some benefits, just a couple bullet points here. Obviously, first and foremost, there is no idling of resources. As I've mentioned, the multi-core computers that we have today, not using those resources is just wasteful. And being wasteful is just generally a bad idea. The user experience. Today, users have a certain expectations of performance. If you have a loading screen, I still should be able to close the window. Nowadays, nobody would wait for your app to load before they can press the next page. So you can only achieve that if you have a multi-threaded environment. And obviously, what I like about concurrency as a whole is that because it's so complex, it really forces you to care about abstractions and best practices and try to minimize complexity of your code in the first place to take care of the concurrency because it's complex enough. So obviously, there are not just the good parts in concurrency, and there's going to be some complexities to it. Some complexities that we're all aware of, it's obviously the thread safety, the liveness issues when you have multiple threads trying to share the same resource, the starvation, the racing conditions problems. So those are something we're all aware or encountered in production. I'm most certain of it. But also performance. This is actually something I'd like to point out, especially to managers, because if you have a single-threaded application, they sometimes go to you and say, oh, let's just add another thread and make it twice as fast. Applications don't work that way, unfortunately, and it will take really time to tune your applications, and it might be not even possible in the first place. And also, the concurrency actually shapes your whole software development life cycle, whether it's testing, development, or even deployment. So it really adds complexity and learning curve to those. So yes, the concurrency is complex, you can't deny that, but at the same time, as I've mentioned, it's beneficial. And I would even go further and say it's beautiful to some extent. And you might think that it reminds you of something that's so complex, especially when you don't know about it too well. But if you learn about it a bit more, you start admiring and see the beauty in it. And the way I like to compare concurrency is the sharks. To me, concurrency is very much like a shark. And the way to describe it, the best way I found personally, is that when you first entered the world of concurrency, and you probably read this book, The Java Concurrency in Practice, when you just start reading it, you face with uncertainty everywhere. Like if you ever thought of Java, being executed top to bottom, where time and order exist, after you just read a couple of pages from this book, you realize that order doesn't matter anymore, unless you force it to be the ordered and timed. The same way when you read this book by John Marie, where he describes the books, the sharks. You would face that they are, dangerous creatures, especially if you've seen Jaws in the past. But then as you read more and more about concurrency and about sharks, you see that how complex the concurrency is, and you start admiring it the same way you would learn more about sharks and realize that they are actually incredible creatures in the first place. So that's actually something I try to tackle today. This is why I call this talk back to the completable future, because we'll start with the fear of concurrency that probably most people have if you've ever dealt with runnables and threats in the past, and we'll try to go from fear to the admiration. And this is where we will focus our journey on. So we'll go back to the completable future, back to the concurrency if you abandoned it in the past. So this journey for us, I'll draw the agenda from here. So first we'll talk about the single-threaded environment and how you can apply the concurrency best practices even there. Then we will move on to the multi-threading model. So far these two steps will be language agnostic. You can use them whatever stack you have. Then we will move on to the concurrency in Java, more specifically, since this topic would be around Java applications of concurrency. And we'll finish today's talk talking about workflows and asynchrony in Java in the first place. So, to begin our journey with the single-threaded environments, I'd like to actually answer your question that why do I even care? I already highlighted a couple benefits versus motivation arguments, but you can still say things like, my app is a single-threaded, I don't care, it's too complicated to even start working with threads, or, this famous, if you have a legacy system, if it's not broken, don't touch it. Even if you have that mindset, it's totally fine, but as long as you apply something called design for concurrency, regardless of your environment whatsoever, you can use these simple rules and simple practices to enhance your architecture. So first and foremost, you're really trying to avoid programming by coincidence. When you write your code and you don't really know how it works, or you're using the library and you just make an assumption how that library works in the first place. You've never read the documentation, you just seen a couple answers on Stack Overflow, and you just rolled with it. So you're really trying to avoid that. And you can avoid that, obviously, by reading the things I just mentioned, or try to apply design by contract. Very simple concept. If I were to describe it, if you're employed currently, and you have an employment contract, in your contract you would have defined responsibility that you need to perform the work for your employer, and you also have rights defined. And your rights would be something like get paid, get certain perks, and so on and so forth. API that you write, it's the communication method. It's the same way you have contract with your employer, you have contract with your consumer, if you're a developer, and vice versa. So if you create a method, and you say, the arguments my method accepts should be of type integer, and they should not be nullable, that's your right as an API owner. But you also say, my API produces non-negative value or non-nullable value. This is the responsibility from your side. So that's what design by contract is about. Another thing you're really trying to avoid is so-called temporal coupling. The idea where you have state of your class change drastically depending on the method or operation that was executed on that instance is something to be avoided. The good example would be, the GET requests. If I were to think of some example here. For example, if you were to try to get the body of your request, before you actually executed that request, you would get nothing. But if you execute the request, then you would have something in return. And that execution is where temporal coupling comes into play, because it changes the state of your instance. And you're trying to avoid it by following the simplest principles we have of atomicity and immutability, which I won't talk in more detail because I hope we're all aware of those. Basically, keeping the state static throughout your methods and keeping the methods and APIs you write focused on a single responsibility that you assign to them. So that was like a single-threaded environment. You can apply those practices regardless of your app. But going to the multi-threading, what I like to talk about first is what kind of forms it can take. First form I'd like to talk about is concurrent form, parallel form, and I'll wrap it up with the asynchronous form of multi-threading. And to talk about the concurrent form, obviously, it's the very first one. it's when you're trying to tackle multiple tasks that hopefully run in parallel, but you have to highlight that they run logically simultaneously, in the sense that they don't require multiple CPUs to be in play. Especially before, where we didn't have multi-core desktops and computers, you would be able to just interchangeably run your multiple tasks, and it seems like it runs in parallel, but in reality, the resource is just shared across those two tasks. So in terms of like the diagram, it will be simple, just trying to run multiple tasks. But this is, I would say, way too abstract, and I like to be practical. So let's actually have an example here. Imagine you're trying to develop an app. And to develop an app, you need only two things, I would say. You need the coffee, and you need the laptop. So you have those two things, and we have an engineer named John. John is a simple guy. He only has a single line of focus, meaning that he can only do one thing at a time. He can drink his coffee, then he has to put down the cup, grab his laptop, do some coding, put down the laptop, grab the coffee, and so on and so forth. And ultimately, he completes those two tasks, you can even say simultaneously, throughout the day, completing both of them, but he has to change the focus that I've mentioned. He has only one. Think of it as one CPU. So that's basically the concurrent form in action. If you were to compare it with, for example, the parallel form, that one is slightly different. And it's different in the sense that it's still trying to tackle multiple tasks. Some people like to define it subtasks as well, which would have to run physically simultaneously, meaning that it requires you to have multiple CPUs. Again, as I've mentioned, people like to define it sometimes where you have a single task, you split it into two. When they're both done, you have the task completed. But going back to our developing app example, you have, again, coffee, you have a laptop, but now you have Jenny. And Jenny, she is ambidexter. Ambidexter are people who can use their hands independently, so they don't have to switch the focus. In that regard, now Jenny has one line of focus and then a second line of focus. So she is able to drink her coffee and also code at the same time. So as a result, she can complete both tasks in parallel. Completely independently, she has to have those two CPUs or two lines of focus, and ultimately she completes both of them and develops an app. So that's the difference in practice. But if I were to talk about the asynchronous form, that one is a bit different. The asynchrony follows this fire and forget pattern, where you have non-blocking operation that obviously would require multiple CPUs because it cannot block your main task at hand. And diagram-wise, it would look something like that. The good example I like to bring is a little bit different from developing an app, is, for example, if you go to the ATM and you're trying to withdraw some money as a customer. So you're withdrawing the money, and as part of the transaction, at the very end, the ATM sends a request to Splunk to log the operation. But Splunk happened to be offline. The fact that Splunk is unavailable and that logging process failed should not block the customer from withdrawing the money. That's what fire and forget would be, where you fire that event to log the operation, but it's not blocking the main task of withdrawing the money. So that's basically the fire and forget in action. But going back to our developing an app operation, to be concise here, again, you have coffee, you have a laptop, but we're back to John. And John started asking the question, where does the coffee come from? That's a good question to ask, actually. Fortunately enough for John, he has a colleague named Henry, and that was Henry all along who was making coffee, brewing it all day long. Probably that was why Henry was hired in the first place. So John still keeps drinking coffee, developing his application, and so on and so forth. But then Henry comes along, and Henry just brews coffee non-stop. The thing is, Henry already made so much coffee that John is not blocked, but John still needs that coffee to be done at some point. So while he's not blocked, Henry's work still matters. So that's basically the three forms in action. Now, these two first steps in our agenda were language agnostic. Now we kind of established the context of concurrency, and we will move on to the Java applications of so-called concurrency. So first there was obviously these two guys, the runnable and the thread. And this is where the problems actually start surfacing. As I've mentioned, many people probably faced these runnable and threads in the past, and this is why they stopped working with concurrency, because they realized how difficult it is to manage them, to create the threads, to properly assign them to the tasks, and especially kill them after they're done. And so, but I still have to refresh the memory of what those classes are. Runnable, it's basically the unit of work, which takes no input, gives you no output, and throws no checked exceptions. In terms of just a quick example, drinking coffee, you have a developer drinking coffee. Ultimately, you need to just override run method, and then you execute it. This does not trigger it in a separate thread, obviously. This is just a unit of work. In order to trigger it in a separate thread, you would have to use something called a thread. And threads they also runnable based. And you always have to think that there is at least one thread in your application. It's a couple, but this is at least one main thread. And again, it's an example. You send down the drinking coffee operation into your thread. Then you try to run it. Does nothing. You have to start it. This is where the magic happens. This is where you spin off the separate thread, and it just goes on, and you have to manage it and take care of it. This is where complexities usually come in. And one thing I have to mention is the creation overhead. Threads are not as cheap, especially on the scale. So creation, destruction, reusability of those threads, this is something you would have to manage in the past. Fortunately, JDK 5 changed it quite a bit. JDK 5, I believe, was released in September 2004, so it's been quite a while. So if you haven't looked at the concurrency since then, I would strongly advise you to. But as I've mentioned, the concurrency API was introduced. And the concurrency API had lots of different new classes and operations implemented. But a couple I'd like to highlight is the ThreadLocal, the atomic operations that they introduced, the thread safe collections, and obviously there are a lot more. We'll focus on these three first. And when you talk about the ThreadLocal, it's a very simple concept in a sense that it works as a resource confinement, meaning that, for example, if you had this famous, people like to complain about this class, simple date format from all Java packages, which is not thread safe, meaning that two threads cannot safely use it as a single instance of a class, because under the hood there is a calendar and so on and so forth. The way the ThreadLocal works, it's something like a map of a thread to the instance of this class. So every time a new thread comes in and tries to grab this ThreadLocal instance, it would create a new instance of the simple date format of the thread that tried to request it, and would keep reusing that instance for the same threads. So that thing I've mentioned where you would have to synchronize on your class, manage the different threads access to your resource, here it's handled for you. And you can just easily use your regular method without synchronized keyword. But you still have to be aware of things like memory leaks, because if you have so many resource instances, you need to take care of them. And it might encourage you to do the ANSI pattern of having lots of global fields. You might be let's just have everything ThreadLocal static on a class. You should not have that. So always be aware of those. With that great power comes great responsibility. So that's the ThreadLocal in a nutshell. But going to the atomic operations, those were created to tackle common problem of compound operations, where you have multiple steps to perform a certain action you want. For example, if you have a collection, you need to check the collection for a value, get that value, make some changes to the value. Those will be three different operations. And as I've mentioned with concurrency, you don't know what the order will be like. So to tackle it, the atomic operations were introduced. They would give you higher speed than regular synchronization, and they have something called compare and swap under the hood. But ultimately, example-wise, if you ever use this inline incrementation of your variables like I++, this is not thread safe. And to tackle that, you have just a single method on this atomic long increment and get. So as I mentioned, the I++ is not thread safe because it has to get the variable value, increment by 1, and reassign it back to the variable. It's 3 operations. And obviously, there are different kinds of atomic operations in that regard. But if I talk about the thread safe collections, which I'm pretty sure even if you don't work with concurrency as much, you've seen in the past, particularly the concurrent hash map, which has been quite popular. If I were to look at it, it again tries to tackle the compound operations problem with a better speed than if you were to synchronize it yourself. And it also allows you to configure certain concurrency settings of your collections. So if you were to do it in the past, you have a map. In the map, you have, for example, you want to count how many times a certain process was invoked. So you would have operation like this where you do synchronize keyword on the map. To clarify, synchronize means if two different threads tries to access this block of code, while one thread is using this block of code, another will be just idling and waiting for the first thread. Again, idling, the problem I've mentioned we're trying to solve. So this looks quite verbose. But with concurrent hash map, you would again have the concurrent hash map instantiated, and then that's it. You don't have to use any synchronized keywords anymore. You just put it if it's absent, and you increment it. And since this counter is by reference, it also updates the counter in the map. So you don't have to do any synchronization on your own. So you can compare the two, and you can see how much less verbose and hence easier to maintain and less complex that code would be. So that's basically just general what we had in the concurrency API. But now if I were to focus on the other piece of the concurrency API, it will be workflows. And I can't talk about workflows without establishing the small agenda for that topic as well. So the words workflows, obviously the good place to start is to look at other solutions out there. Obviously promises in JavaScript is something that have been looked at in the past. I'll talk about futures and callables. And then I'll discuss Executor Framework. And last but not least, obviously the completable futures. So to start with promises in JavaScript, I won't spend too much time on it, but ultimately the problem they try to solve is that you would have to have an operation of some sort, you're fixing a bug. And then inside of that operation, you would have to tackle and handle the result of that fixing the bug operation in a certain manner. So you would basically violate a single responsibility principle, where your method, not just fixing the bug, it also has to take care of execution of on success or on a failure. This is just ugly. And I'm not even talking about the callback hell here. So this is what they had before. Promises were able to clean this mess up. So now they can have the fixed bug operation to itself. And then they would be executing it in this fashion. This is what you would call workflow, in a sense that you finish the first chain of your workflow, fixing the bug. Whatever result it produces, it goes to the next step. In this case, it's then. And it would know, have I failed? Have I succeeded? Let's do, start again or go home if I was successful. So that's what promises allowed us to do. And if you were to look at Java now, how they try to tackle and implement it. If before we had runnables, which were units of work for threads, now we have callable as a unit of work for the future. So when it comes to callables, they're a bit better than runnable. They still don't take any input, but they produce the output, and they give us the checked exceptions. An example would be, I would fix the bug in the future. So I just say, I override the method call, and I say it returns me the result, depending on how I failed to fix it or I fixed it. And obviously, going back to the JavaScript example, I would handle the result appropriately. But on its own, still, callable doesn't do much. It doesn't spin off the new thread. It's just a unit of work. It needs its future. So future consumes the callable. And obviously, futures completed in the future. So they don't block you, at least at the beginning. And they use something called Executor Framework to be able to interact with those future threads. So Executor Services, I'll talk about them in a moment, but just for now, remember that they just execute the unit of work and produce you the future. So you initialize your service, then you have that famous promise every developer makes at some point, I will fix this to-do in my code. So you create this unit of work. Then you say service.submit, you send the callable to it, and it produces you the future. At the moment it goes to the submit part, this is where the work, the execution of that call gets started, but it's not yet blocking your main flow, your main thread. And if I wanted to get the data, I would call a get on the future. So Future sounds great so far, but you might be asking, how do I even use it? These executor services I've mentioned, we really need to talk about them. Executor Framework. So Executor Framework is a great addition to Java in a sense that they take care of thread management for you. Those complexities, they're going towards the declarative model where you really focus on your, action, the task at hand. You don't really care about how do I manage threads, how do I reuse them, that creation overhead. You let someone else handle it. In this regard, it's an executor framework. And it's not very complex, the diagram-wise. We would only focus on something called thread pools. And the thread pools, again, they're the ones that take care of thread management and also thread configurations, like how would you name your thread in the logs and other configurations. But if you were to look in the actual Java code in the constructor, it's enormous. 6 arguments make me cry every time I see that. And so, you can define how big the pool would be, how long the threads live after they're done with their work, and so on and so forth. Fortunately enough, the executor framework, again, it's about declarative model, so this too many arguments problem is tackled by the factories that the executor service provide you with. So executor factories, there are a couple. Single thread pool, it's a great start if you're just writing your code the first time and you want to just verify that it works. There is something called cached thread pool, which is great if you have n number of tasks, short-living tasks, like you write in a crawler, so you don't know how many URLs there are. But those scanning pages usually doesn't take that long. You have something called fixed thread pool, where you know exactly how many threads you would need. It's usually for longer processes, like computations or search of some sort. You have a scheduled thread pool if you wanted to write your own, cron scheduler or monitoring service. And there is something called work stealing pool, which is used by quite a few frameworks, quite a few APIs in Java under the hood. So, if you combine the executors and the thread pools together, you have something called Executor Service. And Executor Service is what actually allows you to have those asynchronous tasks, those futures. And they also provide you the power of thread pools under the hood. So if I were to, again, create my crawler service, I would have something like that. Again, I would initialize new cache thread pool, as I've mentioned, short-living tasks, and I just iterate through the collection of URLs, and I send down the operation to scan them and produce me the document. At this point, nothing is blocking you. It just executes as many threads as there are URLs, and it will handle it on its own, it will reuse threads, and so on and so forth. So that's the executor service in a nutshell. But you might be asking yourself, so we know how to create futures, we know how to use them to some extent, are we done? Unfortunately, we're not. So futures are not perfect. And the pitfalls, the common pitfalls, and why we even this talk called back to the completable future and not back to the future, because there are pitfalls. First and foremost is the blocking operations. That's the major problem in future. There is no real result chaining, so there are no actual workflows. There is no way to combine the futures, and the exceptions handling is fairly complex. So if you were to start with the blocking results retrieval that futures provide you with, the get operation, when you're trying to get the result, if the task is not yet done, you block the thread that you're in. For example, our website crawler produced me the future, but I can't wait anymore, I want the data right now, and I make a call get on it. If the scanning is not yet done, everything just gets blocked, and I have to wait for that process to be done. And I've mentioned it's a bad solution here, because if you ever have to do this blocking operation, you always use a timeout. So go with the timeout if you have to. If you ever have to use the futures, always specify how long that retrieval would be going for, otherwise you block yourself forever. There is no real workflows, as I've mentioned, no future chaining. So again, imagine you have a Kanban board, you have a team to work with, and that team just has a couple of developers, testers. So in this example right here, in this piece of code, the developer is writing the program, as I shown here, the future program, then I do program.get. While that get retrieval of the program, completion of the program is happening, everyone in the team is just idling. They just wait for that single person to finish their code. After that's done, tester picks up the code. So again, I say, the Kanban board, submit, task, tester, test the operation, test the code. And while we're waiting for the tester to finish testing the code that just was written, the entire team idling again. So you can see that there is no real way for specifying this asynchronous flow that the tester would pick up the code only when it's actually written. Instead, in this scenario, we're actually just waiting, blocking, so we're back to our threads, basically, in this case. And you can obviously handle it by going to the callback hell, not even going to go there. The futures combinations, there is no real way to combine futures very well. There are nice operations like invoke any and invoke all, but they're still blocking. For example, you have a collection of integers of some sort. And you have a value you try to find. So what you would do, you would create two callables, which would be two different ways to search for the value, like linear search, binary search. And then you have your service, the search service, and then you say invoke any. In this scenario, basically what happens, we start both processes, both futures independently. So they start looking for the value in this collection. And whatever callable find it first, I will get the result from whatever completed first. So in that scenario, I don't really care, linear search or binary completed first, I only care about the result. Hopefully the result is the same for both. But that invoke any process is blocking. So again, we're back to the blocking operation. And exception handling, something we have to deal quite a bit, debugging, exception handling. And there are always multiple exceptions on most of the operations when it comes to the future. So even if I try to do simplest thing like logging the line of some sort, I would have to take care of at least 3 different type of exceptions in a different manner. Obviously, the interrupted exceptions are fairly simple. We all know how to handle them. The timeout exception is, again, fairly simple as well, but you have to handle it differently. And the execution exception is actually fairly complex, and this is what's coming from the Executor Service. And to take care of that is actually complex. So this is not very developer-friendly, I would say. So there are a lot of issues you can see, but fortunately, we have completable future. Completable future is awesome. And to talk about completable future, you have to just highlight a couple of main operations they allow you to perform. They allow you to transform, to compose, to chain the operations, and combine them as well. It was achieved by completable future implementing the future, so it has everything the future has, and also the completion stage, hence the name completable future. So if you talk about the completable future, we'll really try to go back a bit to how we try to tackle those pitfalls, the pitfalls that future has, and we'll try to approach them and solve them by using completable future. So, in order to handle them, we'll have to start with the transformation and chaining, the real workflows. This is the first time we actually have workflows in place. Okay, here, as I've mentioned, the workflows is the main goal of this class, and under the hood, unless you specify differently, it uses something called fork join pool, as I've mentioned before. So, imagine you have a developer that writes some code right now. So that's the main thread. Now you start making the coffee. So this developer doesn't have to stand up from their desk and go to the coffee shop. They just have a coffee machine next to them. They press a button. In this scenario, it's completablefuture.supply async. So they start making the coffee. So they still can continue writing the code while coffee is being made. And only when the coffee is made, developer maybe stands up and drinks the coffee. So that then apply that chaining that I've shown you with promises in JavaScript was finally achieved in Java itself. So this is basically where the workflows come into play. Again, in the Java 9 and beyond that, these sort of constructors and static factories were enhanced a bit. You have to know that you now can actually supply different thread pools. So as I've mentioned, under the hood, this, then the supply async would be using the fork join pool. You can always run it as separate pools. But one danger when you work with your own pool, you have to make sure you close it. Don't ever forget to close the pool. So, if you were to, again, be able to control futures, finally, in the sense that now they're finally completable, hence the name. And it's not just timeouts now, it's the default values you can complete your future with. So, again, we're making the coffee, but not a simple coffee now, it's latte. So you have like the milk, and the simplest way, milk the espresso. So, but you're getting tired of waiting. You can't wait anymore, and just go to the barista and say, if it's not yet done, give me Americano. Just put some water in my espresso and give it to me. So in this regard, you can say get now Americano. So you send down some sort of default value if it's not yet completed. If you were lucky enough and it's done, they would give you the latte. Then you can also come with a different way. Just say, just complete it now. You're doing latte. First step was done, making espresso. Just give it to me, complete, and I'll go on with my day. So now again, you still can use these getters, but you're not blocked anymore if you don't want to. The good thing again is the idea, the fact that you can now combine, have multiple feature control in place. You have something called all off and any off. As I've showed you with invoke any, this is kind of the alternative, but this one is not blocking. A good example I'd like to give is if you have some sort of WebDriver test and you'd like to run it for different browsers. This is a perfect way to use it. Because now you can just say completable future, all off, so start all of them in parallel, let them run, and in this scenario, the only problem is that results are not formatted, in a sense that you can see this all-off operation produce me the completable future of void. The only things I can actually get out of it, is it done yet? Which is great if you're building like UI dashboard of your test being run. You can also check if any of them failed, with exception, or just completed or not. You can also see how many of them are still running. There are obviously ways around it, like to actually keep a reference to the test you send down to the all-off, but it just kind of highlights you that there are some improvements that can be made to the completable futures themselves, so they are not perfect as well. But at least we tackle the problem of being blocked by futures. The task combination is actually a great use case that I'd like to highlight here. Now you can actually collect the results of different futures and only then process them. Whether process them asynchronously, synchronously, whatever way you want. In this scenario, imagine you in a platform team, some backend team, and there is a team A that wants you to create a new API for them. So you say, okay, team A, file request, I'll take a look. But then there is a team B, and I say, team B, file the request. Only when both teams file the request, as you can see, I do then combine method. It means that only after the team A filed request, team B filed the request, only then this by function comes into play, and I start evaluation of both of those requests, and I maybe come up with a plan for the next release, for the next sprint, or whatever you do. So in this quick use case, quick example, you can see how you can actually use it in the real life. So you have a by function, you apply your operation to the both results only when they're both done, and this will produce you whatever you want. Last but not least, the exception handling. The way that, again, the way Java is moving forward is that going towards declarative model. And here is a great example of that. In a sense, imagine you have your crawler service again. You're trying to crawl your website, but oh my God, the website went down. Obviously, the crawling process would fail for you. So what you do, you have to handle the exception. Exceptional is an awesome word. I like the way they name this method. But the idea that it works like try-catch, and the catch clause. So this is exactly the same. Here, you handle, you can either recover from the exception by returning the default value, or fail and propagate the exception up if you'd like. There is also a handle operation, which kind of works like finally, because every single, regardless whether you failed or not, it would have to go through the handle operation. And if throwable is not null, it means it actually failed. And you have to handle it a certain way. So that's basically the idea. You can see that, again, they removed that complexity, those horrible 3 different exceptions you have to handle in a certain manner, those try-catch, especially the fact that you can't combine the exceptions before. Now you can kind of tackle it in a certain fashion, and it looks exactly as in the sequential way you wrote code, the try-catch finally. So the idea that you can use your experience here in practice is a great next step. So last but not least, I have a call for action for you guys. So first and foremost, as I highlighted, I really like you to embrace concurrency. The fear we all had before with the runnables and threads, as I've shown today, just with a couple of examples, things change drastically, and they'll continue changing. And try to review your application. If you're writing code and still single-threaded, try to use design for concurrency principles to the very least. And last but not least, continue your learning process. The concurrencies keep moving. The reactive programming has been out for quite some time, which I would say is the next step in learning these concurrency models. So really, don't stop there, and I hope you'll move forward with that. And with that, I'd like to say thank you. Thank you for joining me, and we'll go to the Q&A. Thank you.